Hello everyone. In this video I wanted to sit there and expand a little bit on kinetic energy and work. What is kinetic energy? How does it relate to work? Why do we put them together? And I guess the easiest place to start off with is just saying that kinetic energy is the energy of motion. And it has a relatively simple mathematical formula. We have energy kinetic. This is one notation that can be used, EK, is just equal to the mass of the object multiplied by the velocity squared. A few notes that you might want to jot down is that the mass needs to be in kilograms and the velocity needs to be in meters per second. Otherwise, you're not going to get joules for energy when everything is said and done. So with that, this is just to find the kinetic energy of an object. And that really doesn't relate to work, which is a force times a displacement. Or at least it doesn't seem like it relates right at the moment. So relating those two topics together, work and kinetic energy, we can sit there and take a look at the network that is done on something. And I'm not talking about computers and networks here. I'm talking about the network done on an object, and that's just equal to the change in the kinetic energy. So the network is equal to 1/2 the mass times the final velocity squared minus 1/2 the mass times the initial velocity squared. So this is something that you kind of need to get comfortable with looking at and using and seeing what it actually means. And with that, we will take this a step further as well, and that we know that the network that's done on an object is equal to the net force multiplied by the displacement that that force works over, and the network is equal to the change in the kinetic energy. So therefore we can write this out and make it even more of a mess what it looks like. That the net force is equal to the displacement. The net force times the displacement is equal to 1/2 the mass times the final velocity squared minus the initial velocity squared. And this actually has a lot of applications in trying to get objects to stop, especially cars. So for those of you that like driving, when you're trying to slow down a car, you are trying to change its kinetic energy. You're trying to change its motion. And with that, you have a certain frictional force that you have available to you. So therefore, there is a certain displacement that it's going to take you to slow down. So there is a relationship between the velocity that you're traveling and the displacement that it's going to take you to stop. Because quite often the frictional force, the net force, is sort of constant. I mean, the frictional force doesn't depend upon the weight, it doesn't depend upon how fast you're going. So there's a whole bunch of things that the frictional force doesn't depend upon. That usually remains pretty constant, so the relationship between distance and velocity, assuming the car isn't shedding off pieces, is relatively straightforward, that the distance is equal to the velocity squared, or proportional, I should say, to the velocity squared. And what that means, and what that tells us, is if you're going twice as fast, if you're carrying twice the velocity, it actually takes you 4 times the distance to stop. If you're going 3 times as fast, it's going to take you 9 times the distance to stop. If you're going 4 times as fast, it's going to take you 16 times the distance to stop. So, in part, that's why you can't go racing down, back roads and stuff like that at 100 miles an hour, simply due to the fact that it's going to take a large distance to stop the car. But with that, I would like to take a moment and just sort of quickly derive this formula, this 1/2 mv squared equaling the work. And we know that work is equal to force times displacement, and the force is equal to a mass times an acceleration. And with that, we know that the acceleration is the change in velocity over the time, and that the distance an object travels is equal to the average velocity multiplied by the time. And the change in the velocity is the final velocity minus the initial velocity, and the average velocity is the final velocity plus the initial velocity divided by 2. So when we start plugging these values in to that equation, it starts to look a bit of a mess, but then you start to simplify it. And what you see that comes out at the end down here is that 1/2 the mass times the final velocity squared minus 1/2 the mass times the initial velocity squared is equal to the work. and the 1/2 mv squared, we just say that that's the kinetic energy. And K sometimes also is used just to express the kinetic energy of the object. So in summary, what this really does is, by using Newton's second law, the definition of velocity and acceleration, there really is some calculus here, although I'm presenting it very much in a algebra form. What we've derived is a new form of the second law that relates how a force acting over a distance will change the speed of a particle of a certain mass m. So this has some use in trying to describe the motion of objects. So to give you an example problem real quick, just to kind of show you how this all works and how this all plays together. And again, remember, you're watching a video, so you can pause it and write this down and take notes as needed. But you have a train with a car, or a train car with a mass of 200 kilograms is traveling at 20 meters per second. How much force must the brakes exert in order to stop the train in a distance of 10 meters? So the first thing that we need to find out is how much work do we need to do, and then from that we can relate that to the force necessary to stop the car. Well, the net work is equal to the change in the kinetic energy. This is the final minus the initial kinetic energy. So therefore the work is equal to the 1/2 the mass times the final velocity squared minus 1/2 the mass times the initial velocity squared. And in the problem, again, it doesn't specifically say the final velocity is 0. Well, you have to kind of infer that because you're trying to bring it to rest that it's 0. So this whole first term ends up being 0. So with that, we subtract the 1/2 times 200 kilograms times the initial velocity. Well, initially it was moving at 20 meters per second, and please do not forget to square velocities. And with that, we end up seeing that the amount of work that we have to do to get the train to stop, or the work that friction will have to do, ends up being a negative 40,000 joules here. We're not done with the problem. This is not the answer. This is not the force necessary to bring the train car to rest. This is the work that is necessary to bring it to rest. So with that, what we need to do is then take that 40,000 joules, sorry, that should be joules, is equal to the force times the displacement, and therefore we have a force times a 10-meter displacement, and therefore we need to sit there and divide the negative 40,000 joules by 10 meters, and the force necessary ends up being a negative 4,000 newtons, which means that the 4,000 newtons needs to be in the opposite direction of the displacement. And hopefully that makes sense. If we go back, if we're moving to the right, the frictional force would therefore be to the left, and I don't think that surprises anybody. So anyway, hopefully this particular problem shed some light on how kinetic energy and work sort of play together, or work together. Haha, work together. Anyway, thanks for watching. See you next time.